Now, we will study conditions of interference. You might have experienced in some park when Netaji is delivering his speech. There are certain points in the park, in that ground, you will notice certain points at which the tone would be little lower, and besides that point, you will find certain locations where the sound will be more, you could say, intense, or the loudness will appear to be more. So, these kind of experiences that you come across during speeches of some person, this is nothing but the result of interference. So, interference is the process of superposition of two waves, but the waves must be some specific in nature, not with all the waves. So, foremost condition here is to go through what are the basic requirements for this interference. You see, you should come across this term coherent. Coherent source means a source that produces coherent wave. So, that is very simple. A coherent source is one that produces coherent waves. Now, another question, subsidiary question is, what is coherent wave? Coherent wave means the two waves. If there are two waves, they are proceeding, they are in motion, they are in advancement, but their phase difference is not changing with time. You could say, if the two waves are having constant phase difference, you would call them coherent waves. So, prima facie or foremost condition for interference to take place is the waves must be coherent. That means, they may be having phase difference, but the phase difference should be constant. That means, it should not change with time. Second required condition is, one condition I told you that it should be coherent. Second is, they must be having equal frequency. Equal frequency waves only can interfere. Actually, what we are studying here is interference in space. If the waves are having different frequency and they are coherent, then they will produce the result of beats. That is also known as interference in time. So, we are not focusing on beats. This is right now what we are studying is interference in space, or simply it is called only interference. Two conditions you might have noted down. One is waves must be coherent. Second is they must be having equal frequency. Then finally, their amplitude should be equal or almost equal. You see, it is not essential that amplitude is equal. We will study later on, but I will repeat it again. If the amplitude is equal for the two waves, then interference is going to be quite remarkable and distinctive. It could easily be studied and observed. If the amplitude are a bit different or having a difference, then in that case the interference pattern that you will notice will not be so remarkable. So, you could say for better interference, amplitude should be equal or almost equal, otherwise this is not going to be the essential condition. Essential condition are only two, that they should be coherent and frequency should be equal. Now, how do we classify this process of interference? This is two types. One is known as constructive interference, the other is known as destructive interference. You see, mathematically we will derive, but right now here you must know that when two waves collide this way, they are in the same phase, then the resultant is going to be quite remarkable. Amplitude will increase too much, intensity also. So, this is going to be the zone of maximum intensity, or you might say the maximum amplitude. Likewise, if the waves are imposing on each other in opposite phase, then obviously the resultant amplitude is going to be very small. If they are equal in amplitude, it is going to be almost 0. So, destructive interference simply means that intensity has reduced at that point, that has become quite low. You could say this is the redistribution of energy. Remember, in interference, even at destructive interference also, there is no destroying of energy. It is only the redistribution of energy. You have to emphasize this very point, that in interference, conservation of energy is quite valid. It is only the redistribution, or you might say the relocation of energy. At certain point, energy has concentrated, at certain point energy has been rarefied, but we are having the total amount of energy as the sum of the two. After the complete elaboration of constructive and destructive interference in sound, we have two examples especially based on constructive and destructive interference in sound. One is Quink's tube and the other is stethoscope. In Quink's tube, you see it's a fixed U tube. This one is fixed U tube with two stems through which inlet and outlet is possible. Another U tube is in a position of sliding. This is movable U tube. When some wave enters from here, it has two ways, two options, two paths. One path is this way, the other path is towards right. Now, from both the sides, when the waves again come and superimpose on each other, the final result is going to depend on the path difference between them. You see, initially if both sided paths are equal, then obviously the path difference is going to be 0. When path difference is 0, it is a constructive interference. The two waves will be having greater amplitude. We subject this outlet to one candle flame. If it is a constructive interference, you see the flame will get disturbed. Now, if you just shift it by lambda by 4, the additional path, both sides it is going to be added by lambda by 4, then path difference produced will be lambda by 2. When the path difference is lambda by 2, it amounts to destructive interference. Now, the final amplitude of resulting interference here will be 0 almost. So, in that case the flame will remain undisturbed. Between two undisturbed positions of this flame, the shifting that has been done should be equal to, you see, two successive undisturbed flames amount to two successive destructive interference. So, between them that shifting should be equal to lambda itself. So, by calculating this value, the amount that we have shifted, we could find the value of lambda, and once you know the value of lambda, you could find frequency or the velocity, whatever you require. One should be known, other you can calculate. This is what we call Quink's tube.